Is everybody? Okay, we should start then the session of today afternoon. I am Pietro Silvi. I work at the university in Padua, Dipartimento di Fisica e Astronomia in Padova, and I'm also a member of the Istituto Nazionale of Fisica Nucleare, INFN. Today I would like to expand everything that you have learned so far, but we're going to be a little bit into numerics, into calculations, but in a way different than it has been done in the last 30, 40 years with Monte Carlo. What I'm going to talk about is tensor networks, because we are working in a framework that is much closer, in the Hamiltonian framework in particular, and that's a framework that is much closer to the quantum simulation setting. Eventually, as we will develop the actual quantum simulators that we are seeing these days in the direction of quantum simulating high energy theories, we will need some sort of benchmark tools for intermediate size that is telling us what's going good, what's going wrong with our actual quantum simulator that are running in the lab. And so we need a numerical tool that works efficiently for the same framework that is the framework of our quantum simulators. And this is tensor network. Tensor network are a perfect tool because what they are able to handle is lattice Hamiltonian. It is unclear in what sense tensor network could outpower, yet in which sense the tensor network themselves as a numerical tool could outpower Monte Carlos. Probably in scenarios when Monte Carlos encountered the sign problem that you saw earlier. However, it is a description of a many-body Taylor wave function that is based on entanglement. And as entanglement increases in a system, as it is expected for some states, especially in high energy theories, it is unclear where it is the barrier where the tensor network description for numerical calculation will not work anymore. And from that point onwards, we are really counting on the quantum simulators of the next 20, 30 years. But since we get there, instead what we can use at the moment is to use the tools that we have available, that is the classical computer, to predict the expectations of the quantum simulators of tomorrow. And this is a little bit of basic tool that I'm going to provide you today. If you're interested in this direction, that you can see it as working with many-body systems at intermediate sizes, but you can think about it also as a proof of principle benchmarking of the quantum simulator that we're going to build soon. All right. Eventually, you're going to go into the direction of lattice gauge, but the typical framework where the tensor network formalism is typically defined is any type of lattice Hamiltonian. So we're talking about quantum Hamiltonians where the local degree of freedoms are actually quantum variables. They can be spins, they can be gauge fields defined on a lattice, or any type of fermion or boson field on a lattice. And we have Hamiltonians that are aware of the range. In the sense, the most simple thing that you can think about is you have a lattice and the interaction is nearest neighbor. You can define whatever weird lattice system that you want. Think about 3 dimensions, then I do a body center cubic. I don't know why. Then define a type of interaction that is formally decomposed in this sense, and it acts only on nearest neighbor. This is a short range Hamiltonian. It's the most short form of a short range Hamiltonian. And what do we want to understand about this many-body quantum problem? It's intrinsically many-body because the interactions are in the end all-to-all, because every site is intrinsically neighbor to some other site and they are all interconnected. What we want to know is either equilibrium properties, either for the ground state, so temperature equal to 0, or for some finite temperature state. And the other thing we may want to do is exactly the real-time evolution. This is exactly the same type of scope that we were seeing these days, being able to actually start preparing a state and time evolve to future times. We know exactly that Monte Carlos are a problem for this, because that's for sure you're going to get an imaginary reaction. You don't want to do this with Monte Carlo. You want to do it with other numerical method if you can. Otherwise, you go to quantum simulation. What is the problem of dealing with this kind of linear problem, because it's just a Hamiltonian, from an exact point of view? Well, the problem is clearly known, is that the Hilbert space that describe all possible quantum states explodes exponentially, right? If my single site, and I have this Hilbert space as dimension D, then now to define multiple sites, we have the structure of the tensor product that allows us to put more and more constituents in the system, and in this sense, the dimensions explode exponentially. So exact diagonalization is very, very limited. Think about for the most simple problem that you can think about, qubit. So like a lattice of spin 1/2 or of qubits. If you wanted, for example, to do just 160 sites with exact diagonalization, how much would this cost from the point of view of data information? If you wanted to store exactly the vectors, the vector of amplitudes of 160 qubits, well, then you need 10 to the 50 qubits. But 10 to the 50 is the atoms on Earth. So if you were taking Earth and you would convert every single atom into a perfect qubit, then that could represent a state of just 160 sites of a qubit system. And that makes no sense. Okay, so we need ways to actually represent things in an efficient way. And where in all of this discussion comes the fact that we have an information that can help us on how to simplify things. Here it is. The fact that interaction is short range, it tells us that when you look at degrees of freedom in real space, then you know that things cannot be too correlated when far apart, when spatially separated. And spatially separated, it how many neighbors I have to pass through to go from one to the other. So it's something that is built in inside this formulation, right? This tells us that, well, if you consider a system, my lattice, now I will just do a square lattice. And I consider exactly one of these physical states. So a state that can be either prepared adiabatically, or a state that is an equilibrium state over this infinite lattice. And now I consider a partition, bipartition of the system. This is A, and all the rest is the microphone that goes. Hello. You hear me from home? Hello? Anybody from home that hears me?
Yes, we can hear you.
Okay, it works. It works. Thank you very much. And this is the complementary of A. Let's call it B. Then there are theorems that tell you that in equilibrium state, if I consider the entanglement between A and B subsystem, it will not scale with the amount of sites in A, but it will scale with the perimeter, or like the area of the surface that is cutting between A and B. In this case, it's an area of a two-dimensional surface, so it's a perimeter. Okay, so it scales like d to the -1, where d is the physical dimension of the connectivity.
This is, we have only shown this in one dimension.
In one dimension, it tells you that it doesn't. How does it work? In one dimension, it tells you that equilibrium states of short-range Hamiltonian, their entanglement at some point should saturate, and it does. It could also grow logarithmically, but logarithmic growth is not such a big deal. One dimension is peculiar, but in higher dimensions, this is really the typical scenario. Okay, but then this encourages us to write tailored variational function ansatz that actually follow this rule, that when I consider partition in real space, and notice this wouldn't work if this was K space, okay? When I consider partition in real space, then the entanglement is limited. The entanglement that I describe is limited, and if I find a Taylor variation of wave function ansatz that embeds this rule and it's efficient, well, then I'm basically done, right? Okay. And here it goes. So let me describe the many-body state, as we were saying, as in terms of expansion over the complete many-body basis. So I define a basis for a single site, S1, which goes from 1 to its own dimension. In this case, I called D the local dimension. And S at the second site, and all the possible states at site N. And then the state, a single state, is defined by the tensor of all possible amplitudes in all these indices. So it's a multi-index tensor depending on S1, S2, Sn. And this is exactly lives in the complex field to the D to the N. All right. But what if I actually, you will let me now write the state here as a blob of whatever shape you want with n legs. This is the tensor T, and all of these are the possible indices. And this has a value for each combination of these indices. In this sense, what if I approximate the state to be from this complete form into this kind of form? Okay, this is a bit weird. But this is something that makes sense once I tell you how to convert this graphical representation into actual algebraic operation, right? Like this is how Feynman diagram works. Each element in the drawing has a meaning in the sense of an algebraic operation. But this is much more abstract than the Feynman diagram. So like the line is not a propagator. Here a line is just an index. Specifically, here I have an object like a rank 3 tensor, so a collection of complex numbers that are indexed by 3 separate index, I1, I2, I3, each one having equipped its own local dimension. So this goes to from 1 all the way to M2, the dimension of this own index. And this from 1 to M1, which is its own dimension. And this is from 1 to M3. And this is a collection of indexed complex numbers with indices I1, I2, I3, and how many of this I have. This lives in complex to the M1 times M2 times M3. And then I tell you what it means to do some joining some of them. But it simply means that when I take 2 of these tensors and I contract one leg, it simply means that I'm considering all the products for each possible combination of indices, and I sum over all possible indices of the contracted. This is basically matrix multiplication. It's the generalization to n legs of matrix multiplication. So I'm doing the sum over the index I intermediate, I just call it I, of A, I1, I2, I, B, I, I3, I4, and this is simply the contracted tensor that I get, C. C, which is as 4 indices, as it remains 4 legs open, I1, I2, I3, I4. How is this type of language allowing us to describe useful state in the following way? Let's go back to what you were mentioning, right? In 1D, the entanglement saturates eventually, right? And I don't need to describe more entanglement than a given value that depends on the long-range properties of the microscopical model that I have in mind. And that means I could do the following. I consider the state and do a singular value decomposition. So I would like to bipartite the one-dimensional chain into half sides left, half sides right. Doesn't even have to be half and half, right? I just need a point and take the left and take the right. And then I can do singular value decomposition, and I will obtain lambda I, and then the states to the left in system A, and a set of states with the same index L on the system B, and they are not the same. I can always do this in principle. That doesn't mean that it's efficient to do it in practice, but this is a well-formalized problem, right? The truth is that, what is the entanglement of this? Well, the entanglement is simply the von Neumann entanglement, the entanglement entropy, because the global state is pure. Well, it is the von Neumann entanglement of the reduced density matrix. But if you just do a little bit of algebra, it turns out that the entanglement is simply minus lambda j, sum or j, minus lambda j squared logarithm of lambda j squared, and I can put the 2 in front. So, okay. But then if the entanglement is small and it doesn't saturate, what this tells you is that as the system becomes bigger and bigger and bigger and bigger, I don't need to increase the number of states that enter in this decomposition to describe bigger and bigger state, because the entanglement is basically saturated. It's more or less always the same. And that means that when I'm very close to the thermodynamical limit, when my system is very big, I don't really have to describe more and more states in the left-right bipartition, which means that I just need the same number of lambda i's. And now you can actually see that if a tensor network, you see it already here. Look at this picture. It can be readily translated in the tensor network language, right? The language that I told you here about graphical conversion, right? It just tells me that I have this tensor phi that contains all the information inside here, and the phi tilde that contains all the information on here. And then here are diagonal matrix, which can I draw something like this. This is a diagonal matrix. Okay, but then you see that this tells me that the dimension of this bond, I don't have to grow it with the system size. I can fix a dimension, and this will fix me a precision in describing this amount of entanglement. And the same is true for any bipartition, which gives me a good estimate of what is the ansatz in sense of tensor network that I expect to be a good ansatz for one-dimensional system, and it's this one. Now, every time, doesn't matter where I do the bipartition, at any point here I do the bipartition, I'm cutting only a single link, this one here, and this binds the dimension that it has, binds the entanglement entropy that this state can express at the center, at this bipartition. So the entanglement is lower or equal than the logarithm of this dimension that I call M. The interesting part is that this is true both ways. So if you instead take the families of all the many-body quantum states with the condition that at each bipartition left-right, you have a bound on the entanglement of this form, you have exactly this variational class. It's both ways. These are called, I don't know if you ever heard about them, matrix product states. And they are a staple in simulating interacting many-body quantum model of one-dimensional systems. We are now talking one-dimensional, right? Eventually, we will go many-dimensional, but you have to imagine that one has to design a proper class of tailored wave function in this sense. With this picture, I'm expressing the tensor of amplitudes as tensor of amplitudes comes out as a contraction over all intermediate indices that are contracted away of this data of information. In fact, you could write it algebraically, but it's much more tedious. I could write that Ti1 In is just sum over all intermediate variables R1, N minus 1 of all these matrices, each one with 3 indices, except the first. So matrices at the second side, for example, is a function of I2, R1, and R2. The first matrix is only a function of I1 and R1, all the way A, N, In, Rn minus 1. You see how tedious it is to actually, well, it's much kind of nicer and compact to have the graphical representation. But in the end, when you do the calculation on the computer, you actually have some other point to work. Flexible way, so you have to think in that term. A bit of history. This is not how actually physicists figure out things. There was this guy, Stephen White, who came out with an algorithm for doing calculation of one-dimensional systems in '92. And then it was figured out that the states that the DMRG, density matrix normalization group algorithm, the DMRG could reproduce are actually states of this form. Then in 2004, it was figured out why these states reproduce so well one-dimensional system because of that property of the area laws of short-range Hamiltonians. And from then, since 2004, people have started thinking about in big terms of tensor. Okay, it's clear that if this idea works so well in 1D, we can generalize it to any dimension. It will work fantastic. Well, it works yes and no. And higher dimensions, you have a little bit of issues. And that is, you can imagine of expanding the same design in higher dimensions, right? What happens in 2 dimensions, for example, right? You want to have the same structure, but for a 2-dimensional lattice. So like you have these tensors have a physical link, and then links to its neighbors. And this is, it exists. It's a projected entangled pair state. It correctly describes the area law. It correctly describes states obeying entanglement rules law in 2 dimensions. But the problem is that we don't have available an algorithm that is so powerful in approximating ground states with this tool as we have for 1 dimension. The reason is because no matter how you try to contract this to obtain expectation values, you either find approximate solutions or contracting this will scale exponentially. Oh, speaking of exponential, I forgot to remind you how much we actually gain with this picture. Sorry if I'm skipping back and forth. So, okay, we were saying that originally this object was living in dimension d to the n. Now it lives in dimension m squared d, eventually n times. So much better. Now the complexity is no longer exponential in the number of constituents, but is polynomial in the number of constituents, which is impressively better. In fact, if you're interested, I could explain you the staple algorithm that works with this variational wave function ansatz of state. That is exactly the normalization group. Let's see what's the time. It's now 2:30. We have up to 3:30, I understand. Okay, this will give me like half an hour to explain the MRG. It's an old algorithm, but I will rephrase it in a modern, so like explained using exactly this construct and showing how the optimization problem of finding the ground state is converted into a sequence of quasi-local minimization problems that then they are solved with basically an exact eigensolver on a reduced problem. And I'm going to do this completely transparent on what the model is going to be. And later on, we're going to talk, in fact, about lattice gauge, because all of this started from the fact that we wanted to do Hamiltonians, right? And this is exactly what we're going to do. So we will write our high energy model, our quantum field theory problem in a lattice Hamiltonian formalism. So again, like this morning, it was explained extensively. Time stays a continuous variable, and space only is discretized. This is the problems of the doubling problem having a specific signature for Hamiltonian theories and so on, but we don't care about this. What is going to emerge is that we embed the gauge symmetries that are still emergent in our lattice field model into our structure. And I will show you eventually that we are also able to encode in a very natural way symmetries, including gauge symmetries, into this kind of formulation, which will allow us naturally not to violate them. And so we will make sure that our simulations, either ground state or real-time evolution, to stay in the physical space, so to stay in the sector where all the symmetries are constantly protected, especially the gauge symmetries. Okay, and that will be the last half an hour, let's say. So at the moment, I'll be focusing on the density matrix normalization group, and I will delete a bit. This is actually a good, so this was just an introduction. Took a while, but tensor networks are a big topic. It's a good time for questions, actually. If anybody has some, even from home. By all means, go ahead. I have no clue. Could you give me? No, tell me about these bird tracks. How does it work? Okay, but beside the name, can you give me like an intuition of what's the principle behind it?
You can relate it to by knowing that if you're working a specific representation, that's like the tensor. Exactly. And then the bird track, you can convert into tensor from that.
Okay.
I mean, it's the same thing. It's because once you have a representation, you essentially have a tensor. Okay. So you can just call it bird track.
This may be, I don't know, I don't think I will have time for this, but there's something physical in these indices. You see, these seem just to count a complexity, but there's more to it. On these links leave the representations of the symmetry of the whole group. You remember when we were doing, damn it, I just deleted, the singular value decomposition. Say that you have a global symmetry, and then you number conservation, right? You need that each pair of matching singular value vectors need each one to have a well-defined quantum number of their reduced number operator. So I need to have 10 total particles in my big systems. So when I do in the singular value decomposition, I will have 5 and 5, 4 and 6, but never something like 5 plus 4 and 6 plus 5 in a superposition. So they will never have superposition of reduced quantum numbers. In this sense, this tells you that there is a group representation for each one of the symmetries installed in the subsystem represented by this link onto the link itself. It's fascinating. That's one way to draw it. Like, I think Weichselbaum draws it that way. Not my favorite, but yeah, in principle you could. It's misleading though, for a reason that I will not dwell. Okay, the simple reason is because the degeneracies of the irreps in a representation space are dependent on the irrep label itself. So drawing them independent rails is misleading. Okay, doesn't matter. Okay, promised there would. So this is kind of the modern way of understanding the MRG. This has elements from the review of Uli Scholvok from 2011, the DMRG in the age of MPS. I also like very much this paper from Yuto Egeman, 2014, unifying time evolution and minimization method for that state, which is really enlightening. So what we are doing, where is it? I need propedeutic. There's some didactic here that we will need before explaining the algorithm. Tensor network states have a gauge. There's a set of transformation of the networks that maps networks into maps tensors into different tensors that don't do anything on the state as a whole. And this is why. Because if I have A and B, and they're connected by one link, but it's contracted, and the global state depends only on A and B only through their contraction, because this is a state and they are only contracted by a virtual link, then I can do the following transformation. I can put here any invertible matrix and then its inverse. And then I redefine, I absorb X inside A, X minus 1 inside B. This is my A prime, this is my B prime. A prime is different from A, and B prime is different from B, but the state is the same, because the state depends only from A and B, only through their contraction, and their contraction is the same, clearly. So this is a gauge transformation. Why would I care about it? Exactly like why we do gauges in classical electrodynamics, right? We have a freedom to change our variables that does not change physics. It will allow us to formulate the problem mathematically in the frame where it's easier to make the algebraic calculations, of course. And this will help us a lot, because it allows us to work in an isometric gauge, which is equivalent to do on A, I do a QR, if you ever heard about linear algebra routines, the QR decomposition or the singular value decomposition as well, which allow us to transform matrix A into a product, tensor A, into a product of A prime, and I write a little arrow here, and the matrix Q. And now this A prime has this property that if I contract A dagger with A prime, this gives the identity. I basically took the isometric part of A, and the non-isometric part I detached, and I basically absorb to whatever is on the right. The state is clearly the same, but this property will allow me to do calculations much easier, as I will show you in a moment. The energy. So we want to find the minimum of psi, many-body state, but now the many-body state, it's a variational minimum over the manifold, not of all the possible states, but all the states that are written as a matrix product state with given bond dimension. So I fix the bond dimension M of the ansatz that I was writing before. And I have the variational manifold of MPS with bond dimension M. And I want to do the minimum overall possible matrix product state of bond dimension N. MPS, M, the Hamiltonian, and phi, MPS, and is this sufficient? Well, actually, I also want to be precise, right? So to be completely clean, I should add a Lagrange multiplier and the normalization. If I want to convert this in the language of tensor network with drawings, well, it's just a matter of converting the Hamiltonian into this language, which you have to believe me, it is possible and efficient. Remember the previous Hamiltonian that was super simple, like H, J, J plus 1. It's typically, you can convert like that. Oh, if J plus 1 is AJ, BJ plus 1, and how many you have this? I have K of these. It's always possible to do so. Then you need a bond of K plus 2. It's very efficient. Converting Hamiltonian into a matrix product. But doing the conversion of the Hamiltonian is not ground state, right? We know about this. And therefore, if this is the Hamiltonian, then the energy, it's simply the contraction with the variational matrix product state. Where these are tensors A, and on the other side, I have the complex conjugate and flipped upside down. You can think about this as your operation. Minus lambda, well, the rest is obvious. Weird, but it's well formalized, right? Like these are variational objects, A, I, J, K, 3 indices. And you should find the variational minimum, like these parameters. You should do it simultaneously, but if you have ever attempted to do mean field calculations, you know that you don't have to solve simultaneously the mean field equation for the whole system. You can solve for one side, you found before on the other side, plug. Similarly, it converges now. So I find the simultaneous solution, but I just need to find the solution for one of them, with the others coming from the previous optimization of themselves. So Euler-Lagrange equation. I will do the derivative of this functional here in the variational entries tensor. So in the tensor. Something you can do once you have established the graphical rules, this makes sense. And it actually means the fact that dz in dz star is equal to 0. Thank goodness about this rule. Well, this means simply of taking that same picture and removing the tensor from here. I will also highlight this guy here. Okay, that minus lambda. Weird. But if you think about it, this is an eigenvalue equation. It's really a generalized eigenproblem, because look at this. I could do all of this contraction here and call this effective Hamiltonian. And this is simply the effective Hamiltonian applied to this tensor A in this space that has dimension d times m times n. So the dimension of this is dm squared. This is to be equal to 0, right? It's an Euler-Lagrange equation, right? I've differentiated the Lagrangian with respect to the variable. So minus lambda times. Okay, what is this? This is a weird other operators times A again. And it has to be equal to 0. So the two of them have to be equal. I now use the gauge freedom. And before solving this equation, I change the gauge of all the tensors, starting from the sides, going to the middle, bringing each time the non-isometric part inside and inside. Well, this means that all these tensors are now isometrized this way. Look, this one actually contracts because I have, starting from the left, this is isometrized to the right and this is isometrized to the right. But this is simply the identity. I'm using now this rule here. When A is isometrized this way, and this is isometrized this way. No, this way. And I contract over all other legs beside the arrow, they cancel out basically. You only have an identity. Here's what I have. Then I consider the second two blocks. And this also are isometrized, which means that this is also equal to the identity. It's a matter of doing a few calculations so that this part actually cancels out. This part actually cancels out. And here you are left with a true identity. And what's this now? This is an equation. Of these solutions is the solution of the original problems, because remember the Euler-Lagrange problem approach tells you that you will find a set, and then one of them will be actual. But look at it. These lambdas are actually the energy, right? They are actually energies. Equal to lambda, the lambda are actually energies. Which one is one that minimizes the Hamiltonian? The one that finds the ground state of the resistance. Okay, so I diagonalize the Hamiltonian and find the effective Hamiltonian, which is this weird contraction, and find its state. How do you do it? With Langshot. Power method, basically apply H minus an estimate of its ground energy to the -1, and then you apply it many, many times, and eventually all the excited states die, and you only are left with the ground state. There are more preconditioned good solutions for this, for the Langshians, that is the Arnoldi. Arnoldi is a better Langshius. You find packages for doing linear algebra routines like these Arnoldi everywhere on the internet. They are encoded in Fortran, in C, in whatever you like, in Python. This can be done. You found the ground state of the effective Hamiltonian, then you plug its solution, solving. Then you move to the right, you change the gauges, so that now you're gauged with respect to the site, and you solve again, and then you move right and left. You sweep 6 times, typically it's enough, and you converge to the global ground state MPS. So the MPS that minimizes the functional, and it's a great approximation for the ground state. The only question that I left unsolved is this efficient to calculate this effective Hamiltonian? I have to show you that I can do it in polynomial time, because then I have to diagonalize it. If this was as complicated as many-body exact Hamiltonian, that this wouldn't be efficient, but this is extremely efficient. Because say I already absorbed up to here, and I have calculated this object that is a tensor m times d times m, and I want to eat another layer of this compound that I'm calculating from the left to right. Well, then I have to contract it with my MPS block, and this costs m3d squared. Trust me, it's like matrix multiplication. When you the most brutal way when you're multiplying two matrices, this m times n, and this is n times o. The matrix multiplication costs m times n times o. This is brutal. So this costs m times d, so m3d squared. Then this is not actually d, this is k. So m3k k times d. Then I have this, that is this does not exist anymore, k dd. So m2 k2 b2. And the last one, this does not exist, this does not exist, M, D, K, M, N. So again, like this. And of these two, the dominant one is definitely this one. So my algorithm scales only like M to the cube. M was my refinement parameter. So how much entanglement I want to describe. Remember, the entanglement that I can describe of any bipartition is the logarithm of M. That means that if the entanglement saturates, I don't need a very big M. There are typically considered, even in the most complex scenarios, are never more than 1,000, 10,000. So that's totally doable on your laptop. You don't even have to go to petabyte supercomputer scaling. Of course, on a supercomputer, you can launch something 1 million of simulation at once, so it's helpful. Once you have found the solution, your grounds that you can do all possible queries, calculate all endpoints correlation functions, which you bring your experimentalist in the lab. And here is what you should get on your quantum simulator, and they can compare and see how much they are far away, because typically the error that you get from this are 10 to the minus 15. So the errors from this are incomparably small with respect to the errors that the quantum simulator do in this era. Maybe one day.
I was saying, it's been a while, but I thought the optimal power for matrix multiplication is like 2 point something.
In fact, this is an overestimate. It's true. It's not like this, it's better than this. It is correct. Sorry if I don't go into this level of detail, but yes, you can do a bit better than that. Because matrix multiplication, you can do divide and conquer, which does not cost as the product of these three, but it's 2.83, but if the three of them are the same, if the 3 dimensions are the same. So for multiplying 2 square matrices. No, it's less, but then you have to decide what exactly is the scaling if these are rectangular matrices. It's not so well defined if it scales in the same power in all 3 dimensions. It's tricky. No, but it's true. It's a bit better than that. Okay, so this is the algorithm, and to be honest, the only property it relies upon it's that you have to be able to write these effective Hamiltonians and contract them efficiently. All of this relies upon is the fact that the tensor network itself must not have closed loop in the geometry. So as long as your tensor network does not have a closed loop of links in its geometry, you can do an obvious trivial generalization of this algorithm, which will work for that geometry. We actually do that, and that is one way to actually tackle higher dimensional problems. Because now, let me give you this example. Now we don't do any more matrix products. We're in a different state. A state that is similar to a tensor network ansatz wave function that is similar to a real space renormalization. This is a tree network. It has the same principle as matrix product state, but you have the usual properties that each partition in real space that corresponds to a cut in its geometry has entanglement bound by this cut. But you see that now it's a much more fractal structure than before. Earlier, each left or right bipartition had entanglement perfectly bound by the same amount. Different because what if you cut, say, from here to here? It's a bit weird. But this is not as well behaved in the sense of RLO as the other. It can be generalized to any dimension. You see, if I want to do a 2 dimensions, like 1, 2, 3, 4, 1, 2, 3, 4, 3, 4, 1, 2, 3, 4. And then I first renormalize horizontally. Then at the second level, I renormalize vertically. Okay, can you see the two-dimensional? Maybe not super. You can have a two-dimensional renormalization. First horizontally, then vertically, then, and so on. And with this, we have a tensor network structure, a wave function that is now does not have loop in its geometry. So we can do an equivalent algorithm that DMRG. Unfortunately, it does not respect area law for two-dimensional system, but it's still better than in field. It is clear that this won't be able to represent everything, but if I go to an intermediate size, 8 by 8, 16 by 16, this can still much better represent the system than mean field and work at sizes that are still not accessible to exact diagonalization and give still some prediction that you can give to your favorite experimentalist that is running the quantum simulator. And at least you have a better prediction than a mean field prediction, which is, so to speak, not so bad. To be honest, we actually managed to predict the Coulomb phase in 3+1 dimension with this kind of ansatz for 3+1 dimension for quantum electrodynamics model with the Cogwood-Susskind Hamiltonian. But that was mostly advertising. Maybe if you're interested, I can show you something. I have some slides. But I think it would be more didactical in the last half an hour to show you how all of this machinery can match the interesting properties that we have in high energy models, so in lattice gauge theories. And again, we're talking about Hamiltonians, so we're talking about lattice gauge theories in Hamiltonian formulas, something that will make your experimentalists happy because it's close as possible to their setup. Another good moment to ask questions.
Yeah. I'm wondering if you're being coy or it's true. Are you only able to do open boundary conditions or ask for periodic?
No, okay. No. Okay, so problem matrix product states have a problem with open boundary conditions because of the loop. So the meaningful generalization to periodic boundary of 1D of a matrix product state is a matrix product state that wraps around. This generates one loop that is the loop of the periodic. This unfortunately is a mess. It creates a lot of problems that White himself has dealt with for 10 years of his life, and he damned himself the time he spent on this problem. But you could think about not going in the direction of matrix product state. In my opinion, the best way to do periodic boundary condition in 1D is this one. We have actually shown topological, symmetry protected topological phases in the bilinear biquadratic model in 2014 with this ansatz. No chance to do that with matrix product states. And those were definitely properties of periodic boundary condition because it was SPTO. In higher dimensions, I would use still this one for doing periodic boundaries. In higher dimension, there's the usual problem of periodic boundaries and gauge fields like electrodynamics. You cannot put finite densities and periodic boundary conditions, right? Because you have the surface that has to have a flux, but how can you have a flux if you have periodic boundary? So that cannot be done. So like in quantum electric theories that have a charge and a Gauss law of the type that preserves a charge, a scalar charge, you cannot put periodic boundaries anyway because it doesn't make sense if you want to do finite charges. If you didn't have this problem, I would go this direction. we have shown with this method in 2D in 2016 topological character of the Harper-Hofstadter model. So it's basically a friend of quantum Hall effect. So that, to my knowledge, is the most reliable strategy. There's the usual problem that we don't exactly describe the correct entanglement distribution with this ansatz, which unfortunately means that we have to crank up the dimensions very much, more than in 1D, more than matrix product state, because we have to adapt the imperfect description of entanglement with more computational power, unfortunately. I hope that this answers. By the way, I was asked to repeat the questions. The question was, what would I do for periodic boundaries? And that was the answer. It was in 3+1. So 3 spatial dimensions. We can discuss about this result. I can show it to you. We found a phase where we didn't do exactly the horseshoe. What we would wanted to do was the horseshoe order parameter. The question, by the way, the question was in how many dimensions was this Coulomb phase? So we want the horseshoe order parameter. But for time constraints, we couldn't. So instead, we pinned 2 static classical particles and we let the electromagnetic field plus fermionic excitation to adapt themselves to its own ground state configuration, and showed that as a function of distance, you would not get a field in between that depends on the mass. Because instead, in the string breaking phase, the points at which you break the string depends on the mass. The stronger is the mass, the faster you break the string. No, the stronger is the mass, the later you break the string, right? Because you have to create masses to break the string. And so you create longer and longer strings before you actually break them. In this other phase, we always find the same behavior no matter the mass. And so we argued that this was the best signature for the Coulomb phase.
Okay, so here the bond dimension n is always fixed, so you can't do something like get in.
Yes. Okay, I think I understand the question. And the question, let me phrase. Sorry if I don't use the same words that you use. Is like how it's actually chosen. Okay, what's the actual way to tune properly in? So like. Typically, when you actually run a simulation, you just fix a maximum value for n, and at the same time, you choose also a threshold for those singular value decomposition probabilities that you have in front, because you almost never get the precision. Right? You don't get the precision beyond the double precision. So you never want to go with singular values below 10 to the minus 8, because then their squared is 10 to the minus 16, and that's basically a numerical 0 compared to the first one. So you choose a threshold, and you remove the states whose singular value probabilities are below the threshold, and if you don't reach it, you hit up to the maximum m that you have allocated for your simulation. And then what you do is show that by taking larger and larger, eventually all the 1-point and 2-point correlations converge with increasing this maximum m. This is the most rigorous way to do actual simulations with tensor networks in general.
Yeah, I guess my question was more if I wanted to do a simulation that showed entanglement growth, would I still have to fix m, or would I change that
You can change the dynamic, like you cannot fix a maximum M at all, and like only base yourself, rely on a cutoff threshold based on the single, because this is something that you do all the time, is actually evaluating your singular values. I showed you the single site update algorithm, which is the one easier to explain. It's not the one that you actually do in simulation. In simulation, you do the two double tensor update algorithm. You consider two of them as actually variational variables. You fuse them together, you optimize this pair, then you open them, you increase the internal ball dimension, and now you cut based on their singular values that you actually found. You can decide not to fix a maximum bond for the simulation and instead base your cutting only on the single values that you get in this procedure. But good luck at succeeding in doing that, especially if you do something like out of equilibrium evolution, because an analog algorithm that I did not show you, you can use the same effective Hamiltonians as Schrödinger integrators to actually do real-time evolution. This is why like DMRG and real-time evolution with tensor networks are basically the same framework. You just have to remember that you have to evolve forward in time for two tensors and then backwards in time for a single tensor. It's weird, but it's the same that you calculated in the MRG, same ingredients you use exponential integrator, complex exponential integrator to do actual time evolution. But time evolution is more problematic from a conceptual point of view, because when you actually do a quench, especially a sudden quench, you have an incredible growth in entanglement. Because when you go out of equilibrium, those theorems that tell you about the area law of entanglement, they fall. They're not valid anymore. And so if you don't have any more bounds on entanglement, you expect that soon the ansatz may break down.
I guess 1D would be an exception because there it's always bounded by something.
Wait, but
in 1D, even if you have a quench, there is an upper bound. So I think if you just use that as your bond dimension, you still should be.
But to be honest, even in 1D is problematic. The problem of generation of entanglement, even in 1D, was taken seriously for many years by Mari Carmen Bañuls in MPQ Garking. And she showed actually that you can see linear growth of entanglement, pre-thermalization and thermalization. And then revival. It's weird. You can actually find the thermodynamical regimes of system evolution, because basically what entanglement tells you is that you're looking at a reduced subsystem, right? Like say your left half. And then you can consider the right half as an environment, but a finite environment. So you actually see all these effects, linear growth, like explosion of entanglement, pre-thermalization, thermalization, revivals. It's really cool. She studies this for many years, and I think there's a lot of literature of that. I invite you to have a look at her literature because she studied it seriously for many years. Okay, I forgot to repeat the question. Okay, the question was, I don't remember, but I hope I hope that it can be deduced from the answer. Okay. Okay, one last thing. Oh, 15 minutes. Okay. I want to talk about lattice gauge because that's the topic of the school, right? Like all of this seems to be completely unrelated. No, let's talk about lattice gauge. Okay. I will show you an example on how do we actually take care of lattice gauge problems. You have to trust me that I don't have time to show you how we deal with global symmetries, but I gave you already some intuition before that links carry a representation of the reduced part of a global symmetry. Something similar is going to happen for gauge symmetries, but in a way that it's a little bit more intuitive to understand. So what I'm going to do is write an actual Hamiltonian. And I'm going to write the Schwinger model. Okay, it's a Kogut-Susskind, but in 1D you don't have the plaquette term, you only have the electric. And I'm going to truncate. Sorry. We're going to truncate. Okay, we can also get Zn subgroup of the group. It's not from the point of view of doing the coding for tensor networks. So, okay, let's put staggered fermions, because in 1D the staggered fermions resolve completely the doubling problem, and it also allows me to use a single fermion population. I'm not going to put any flavors. I mean, we could put flavors. Yeah. So this is fermion field. And then we're going to put the transport, which at the moment I'm putting it with full units, but ignore it. You can ignore it, because all I care about is how to construct meaningful bases for this. And then we put the pure gauge part, which, if I'm not mistaken, in 1D, the A is on top, but correct me if I'm wrong. While for 3D, for 3 dimensions, the A is at the bottom, but in 1D, I believe it's on top. I mean, I'm not an energy physicist, so this is, you can tell me about it. I'm not offended. And this is the electric field square with the obvious. So you were describing the matter field onto the matter side and the gauge fields on the bonds. The gauge sides, which are basically the bond of the theory, side J plus 1. The fermion field lives here, and the gauge field L and U lives here, J plus 1. Usual, where we actually, in order to complete the identify how we define the algebras, and the gauge symmetry is emergent at the moment. And what are the sectors of gauge symmetries that we pick, because that will define the physical space. I know that psi J prime anticommutator 0, psi dagger J prime anticommutator is delta J prime, and U and U dagger commutes to 0, and U and L J prime plus 1 is delta J prime U J plus 1. Okay, these are my algebra rules. One I will break by truncating. Sorry about that. Sorry. What can you do? And then we have to define the gauge symmetry, right? We need to have that the electric field after some site has to be equal to the previous gauge field plus the charge. And when you do staggered fermions, remember how it works, right? For odd sites, fermions represent matter particles, and for even sites, fermion holes represent antimatter particles, right? So here I have actually to write psi dagger psi. This is the charge, but I have to add a constant for even sites minus, so 1 minus 1 to the j divided by 2, something like this. this is exactly what fixes, like tells me particles are fermions here and antiparticles are holes here. Okay, that despite I understand that truncation has problems, for now I'm going to take a truncation of the gauge field, which is based on an energy cutoff, right? Of this term here. You can argue it's going to be a problem towards the continuum limit because this coupling is going to be less and less relevant. Don't worry about it. It has been shown in 2016 by Boye-Booyens that actually this converges super fast. If you want to figure and to extrapolate quantities at the continuum limit, you never have to go beyond a cutoff of 10 states. And you can extrapolate things super good, impressive. But let's consider, for example, I don't know, 5 states. So the state at 0, state at 1 and -1, state at -2 and 2. And then here I take a cutoff at 4, let's say between 4 and 9. So let's say at 6, AG squared divided by 2. And I truncate what's the rest. Okay, what I would like to do now is actually to try and work in an effective space that takes into account as much as possible the gauge degrees of freedom, so the gauge symmetry, and eventually keep a selection rule on nearest neighbor. So what I'm going to do is to double each gauge degree of freedom. I'm going to double it. If the group is non-abelian, you have to think in terms of quantum link models. But for this abelian group, you can think about doubling. And then I define my dressed site basis as the following. I take the fermion site, and then the gauge field to the right and the gauge field to the left. But I will only select the states that satisfy the Gauss law. Specifically, let's list them. For a fermion site, for a matter site, here are all the states that I need to consider. So, states with empty fermion, and they will be -2 quanta of electric field to the left, 0, well, then I must have also -2 quanta to the right. And then -1, 0, -1, so 0, 0, 0, 1, 0, 1, and 2, 0, 2. And then there are the states with instead the full fermion. So I have -2, 1 fermion, matter fermion. So this gives a charge of +1. -1, -1, 1, 0, 0, 1, +1, 1, so +1, 1, +2. These are all the states that satisfy my Gauss law for a fermion site. So in this dressed basis, my dressed site of the simulation is 9-dimensional. So t equal to 9. The local dimension is equal to 9. But now I don't have anymore this weird AB lattice type. It's only a simple, now it's a simple lattice, dressed site, which I actually will draw it like this, a dressed site, and then another dressed site, and then another dressed site, each one dimension d equal to 9. The only thing that I need to still enforce is that when a site I'm in one of these configuration. At site 2, I need to start with the configuration that corresponds to this one, because remember, this is the same degree of freedom. I doubled the gauge degree of freedom. And so I need to, again, to start with -1 and then something like this, anything. This converts into a series, into a set of 1 billion selection rules between nearest neighbors that I can trivially embed in any algorithm for tensor networks. So this is something that comes supernaturally. The easiest way to see it is that each one of these selection rules can be actually written as a matrix product operator. So I can express the violation of these selection rules as an energy penalty, or I can add them exactly into the ansatz. And this will allow me to write and tailor perfectly gauge symmetry within the tensor network ansatz. So respecting this symmetry exactly without any further constraints, hides entanglement constraint. So in this sense, you can imagine, or at least I hope I convinced you, sorry for the confusion of this last part, that tensor networks are a natural way to express states with low entanglement, and then they can naturally embed symmetries. You have also a natural way to embed symmetries that are local, but a patchwork where you cannot separate them all, such as gauge symmetries. And in this sense, we believe them to be the perfect benchmarking platform and compare the quantum simulators for high energy physics and for gauge field theories that we're going to build in the next 20, 30 years. We see where we get with numerics. From that on, the race is for quantum computers. With this, I finish.
Questions?
And I won't show you any results because we are already out of time.
Well, actually, you have a few minutes.
No, it's not worth it, really.
Okay. Any questions? Okay.
There were already quite a bit of
okay.
questions. Maybe somebody from home has questions for me.
I was just wondering about the Coulomb phase thing you meant. Like it's a gapless phase, and it has volume law entanglement. So how are you able to replicate it with the tensor network?
I never said that we were able to reproduce correctly the gaplessness of the phase. We just observe it. I must have it somewhere here. Yeah, I have to do this, I guess. I have to find it, and then no, I cannot share screen now. Is it visible? Okay. Oh my goodness, this will take forever. Sorry. I don't know if it's worth it to. Here we go. Condensator. Here it is. So here I show you those two regimes that I was telling you before. What we did was, let me go back a moment. Consider like the Kogut-Susskind plus staggered fermions. And by the way, Kogut-Susskind plus staggered fermions still has one doubler. Okay, so we haven't ruled out if this effect may be modified by the presence of that residual doubler, but there's still degeneracy too with Kogut-Susskind in Hamiltonian formalism. you find this on Susskind 79 lattice fermions. You show that there is still one doubler left, even if you do staggered fermions, Hamiltonian formalism. And then we simulate that model on a cube. It was 8 by 8 by 8 with this tree tensor network following this renormalization structure. Dimension layer 1, dimension 1, layer 2, renormalized dimension 2, layer 3, normalized dimension 3, and then repeat. And by doing so, with 9 layers, you manage to describe an 8 by 8 by 8. Then we put 2 static charges at variable distance. We put ourselves in that case open boundaries, not periodic boundaries, exactly because these 2 charges, no, actually they were opposite, so we could have also done periodic boundaries, but we wanted to check as a function of the distance. If you put periodic boundaries, the distance is always at maximum half, because then they see near to each other from the periodic boundary. So in that case, we'll open boundary anyway, even though it was charge 0. And then we have verified these 2 regimes as a function of G. And we did not take the continuum. Okay, so this is also important. We did not take the continuum limit because we took the spin 1 representation for the gauge field. Okay, no -2, no 2. This clearly poses some sort of cutoff for the electric part. For the magnetic part, you have the G at the denominator. So that's the smaller you go with G, the less imprecise is the cutoff that you're taking, because you're actually changing the physics. But this is what we could do at the moment. Apologies if that's a limitation. And still we saw this behavior, emergent behavior here. In large G, we see an increase in the energy for these 2 static charges as we pull them apart. We create the static charges just by pinning big chemical potentials at one point and another point of the lattices, where one is matter and the other is antimatter. And in the large G case, we see that the energy increases. In both cases, the energy increases as you pull them apart. But in the large G case, it breaks at a point that depends on the matter, on the mass. The larger the mass, the later it breaks. Instead, for the small G case, it's completely irrelevant of the mass. And instead of having this very discontinuous shape, it has a much smoother shape, which reminds a bit like 1/r. If we wanted to be rigorous, we should have done horseshoe. Maybe next time. I hope this satisfies your curiosity. We can talk further about it.
Yeah, no, I was just surprised because like the volume was very bad.
Yes.
I was just really surprised because the volume loss scaling suggests that your bond dimension is like exponential. So
no, why volume law scaling?
because it's a gapless phase. Right?
That doesn't mean that it's volume law. In one dimension, you know that gapless systems, the entanglement diverges logarithmically, which is very, very different than an out-of-equilibrium system where it actually grows linearly, or a random state where it actually grows linearly with the partition, with the size of the partition. So even for gapless systems, the change in the violation of the area law is very, very weak. In 2 and 3 dimensions, a gapless system can be perfectly area law. It was shown by Ignatius Sirac that a boson gas in 2D and 3D is perfectly area law, and a boson gas by definition is gapless.
Yeah, I guess I was thinking about some generic state, but I guess you need some integrability or something to have.
No, I didn't get
I was just confused because generically you expect volume law scaling for gapless systems.
No. This is a misconception. For gapless system, you can go beyond, above area law, but equilibrium in short range volume law almost never. The problem of PEPs is not that they don't represent correctly the state, the states, either Gapler or gap system. The problem with PEPs is the algorithm. That optimization algorithm or integration algorithm with PEPs are unfortunately approximate. And most of these approximations are uncontrollable, like tensor renormalization groups, TRG. There's an approximation in it and is not controllable by a parameter that can be made as arbitrarily small. So still research and development phase for PEPs. In the meanwhile, we do these tree tensor networks because we have an algorithm.
Other questions? So 15 minutes, right? And then we start.
Thank you.